Today we're going to do section 4.2. So first, let's look at the book. Let's see. We have that is that right? Yeah, like that. Okay, and then let's get a little closer on top, and then on the bottom. That's good enough. All right, next, this is page 124 and 125. Let me hold it back, front, something. Okay, a little closer maybe. All right, and then on top, a little closer on top. Okay, and then a little bit closer on the bottom. All right. And finally, the last pages, 126 and 127. Does that look okay? All right, and a little bit closer on top. Let's see. And on the bottom. Okay. So let's look at page 122, section 2 of, well, whatever. The point is we're doing 4.2, and please read the introductory paragraph on top yourself, okay? And I'll go straight to definition 1. A function has an absolute maximum if of a region means that it is the biggest value in the entire region. Okay, that's why it's called absolute. Now, what does the word region mean? We had the word region, the definition of the word region back on page 13 of the book, and I want to refresh you of the memory because we haven't really seen it for a while. Now, first, remember that a domain in this book is an open set and connected, okay? That's what the joined by broken line blah, blah, blah means. It's an open and connected set. And then a region is a domain that may or may not have its boundary point. It can have all the boundary points or no boundary points. So basically, in this course, we're going to use the word region instead of domain to mean domain. Anyway, yeah, for two-dimensional functions. So that is what that word region means, okay? And so then that's the definition of absolute maximum. And the next definition, the relative maximum, just means that it's maximum in a small area, with a delta distance, okay? But it's in the entire open region within delta. If it is has a relative maximum, then that is bigger than all its immediate neighbors in an open set, and then it will be considered a relative maximum. Again, this is the definition for the maximum. The minimum definition is similar. Now, next, the book considers an example, okay? Please work this example out yourself. What we're going to do is we're spinning some curve around the x-axis, which give us, and then consider is maximum or minimum. So here is, so please plot this thing out in the Desmos 3D calculator. And here's what I did about this example, okay? And the curve, once if you spin it around, then the parametric representation will look something like this. And then the 2D representation, where z equal to x graph, is right here. All right, and then it but we are considering the domain to be limited from, I think, -2 to 2 or something like that, or x squared. Oh, I know. We're considering the domain of the function to be within the circle of x squared plus y squared equal to 4. Yeah. That's what I have written down right here. So that's all we care about. Now, within that domain or region, you notice that the function then has a minimum point that is all the way around at the bottom, and so on. Anyway, so please explore this example yourself, okay? And I'm not going to talk too much about it because I think it's fairly self-evident once you look at it long enough. And then it has no oh, my graph, the reason my graph is missing something is so that we can see inside, I guess. Yeah, so that because I wanted us to see there's a slight absolute maximum right here, okay? And then it says there's no relative minimum, and right. Well, let me think. Well, there's no relative minimum because strictly speaking, see, all the bottom is sort of a minimum, but each one is right next to the others, right? So then nobody is the absolute minimum at the very bottom, okay? Because they're always next to somebody else who's also the minimum. So there's no, strictly speaking, no relative minimum. But, well, anyway, because the absolute maximum is defined as bigger than or equal to, whereas the relative maximum is defined as bigger than only. Okay, so yeah. Anyway, so let's move down to theorem 1. So please go over the example yourself. Okay, and the theorem 1 says that let f of xy belong to C1 in a bounded region, and then which has a domain and a boundary curve of the domain. Now first, I want to review what C1 means. C1 is, you remember, is something about, it has first derivatives, right? That's what the 1 means. But it also means, let's see, okay. Here is the definition also on page 13, where C1 is defined as Cn is when the partial derivatives, okay, are all continuous up to the nth. In this case, we have C1, so the first partial derivatives. But well, Cn is just whatever nth partial derivatives, all of them, okay, has to be continuous. So the partial derivatives cannot just exist; they also have to be continuous for this thing to make sense. All right, so that is, I want to refresh your memory of that. It's not a big deal. It's just something, but we haven't seen it for a while. It's a good idea to know exactly what we're talking about. So this thing is in C1, so all partial derivatives exist and are continuous. We don't have to think about them too hard. And then, so continuing the theorem, it says, and then the second statement is significant. It says that a certain point, some point inside the domain, has bigger value than all points on the boundary of the domain, okay? So when you think about a boundary, and then you think of there's a point inside that's just bigger than every single boundary value for the function, that is. If that is the case, then there exists a point in the domain such that it is the maximum. It is bigger than or equal to every point in the domain, boundary included, and then and also the partial derivative at that point, f1 and f2, will be 0. Okay, that is all right, so that now let's read the proof. Okay, first we will say that since f is continuous in the closed region R, and remember that our region is bounded and closed, because the region consists of all its boundary. So then if f is continuous in the closed region, then it has a maximum. This is a theorem that we will prove later, okay? Right now we'll simply accept it and then as obvious. So being that that is true, let's say, then it has a maximum at, let's say, a big X, big Y, which, and this, if it has a maximum, then f of then this maximum then has to be in the region, because there already exists a number that is bigger than all the boundaries that it does include that's in the region. Now, the D is the open set, see, is what the in D means. In other words, it's not just something on the boundary, it's actually on the inside of the region, because we already have a function, has a value fab that's bigger than all the boundaries. So the maximum, which would be at least a bit, should be as big or bigger than fab, would then be in the domain as well. So then, in the sense that the maximum couldn't be on the boundary because there's an interior point already bigger than all the boundary. So the maximum has to be inside the region, that is in the domain D. Yeah, remember the difference between D and R is D is the inside open set, whereas R, the region, is D plus the boundary. Okay, so that's that. So because of that, then let's read the next sentence. Okay, where f of x plus delta xy minus f of xy, if you move out of it in one direction, that will be bigger than or equal to 0 if delta x is less than 0. So what happens here is that any value, okay, subtracted by f x and y is going, the numerator here is going to be less than 0 because fxy is the maximum. Okay, so if the delta x is negative itself is also negative, then see delta x less than 0, then the whole thing is going to be bigger than 0 because this is negative over negative. On the other hand, if delta x is positive, then it's negative over positive, then this fraction is going to be less than 0. So we have this fraction which is bigger than 0 when delta x is less than 0 on one side, and it's less than 0 when delta x is bigger than 0. So then when we allow delta x approach 0, then that proves that f1 is going to be both bigger than equal to 0 or less than or equal to 0. So then we forced f1 to be 0. Isn't that cute? And yeah, so then similarly f2 is also shown to be 0 that way, and that's how the theorem is proved. Yeah, a very slick trick. So next, let's look at the next part, section 2.2. Now, continuing on page 123, example A. The example A is a fairly straightforward example where we are demonstrating how to use theorem 1, especially trying to get it to satisfy hypothesis 2, where some point inside is bigger than or smaller than every point on value of f, every point on the boundary. And once you've done that, then you can establish that it is a maximum, or in the opposite case, minimum. So that's what we're doing right here. Right here, in example A, our boundary is the circle, the unit circle, okay? And then it's pretty quick to show that at the origin, this value is bigger than all the boundary, therefore the absolute maximum exists, and then we take the derivative and then find out that the absolute maximum is at the origin, which is also true if you just stare at it. That function is biggest when both x and y are 0. Okay, so then the biggest value will be the square root of 4. But anyway, this is to demonstrate how the theorem works. Now, example B is a sort of a counter example. That is, we cannot use theorem 1. Why? Because this thing isn't continuous. It has to be, because there's a square root, you have to take the square root, which creates a fraction where things can be 0, etc. So it doesn't belong to C1 in the domain that we're given, which is the unit circle, within the unit circle again. So then, nevertheless, this function still has a maximum at exactly 0, 0, where you can see that by just looking at it, because it happens to be a fairly simple thing. So that's example B. Now, example C is yet another counterexample in the sense that the hypothesis 2 is not going to work, because this is just a plane that goes up, down, and it does not have any absolute max or absolute min, at least not within. Okay, if you draw a boundary, then you will have some kind of maximum on the boundary, but it wouldn't be inside. And then, right. And then, of course, the first partial derivatives will never disappear. So the point is, it's not going to work. And then, yeah, it's, well, within the limited boundary, in this case was confining it to the unit circle. It has a highest point, but that's only because the domain is restricted. And then the partial derivatives don't ever disappear. And it doesn't disappear at that highest point either. And anyway, so that's example C. Please go over this yourself too. And now let's come to example D, which has more involved. The example D, we have some function that is slightly more involved, okay? And the domain, as you notice, is the entire real plane. It says x squared plus y squared is less than infinity, which you might wonder, but I thought we were talking about the bounded region as the domain, right? Why is this less than infinity? Well, what we're going to do is consider in the bounded region in a circle of radius r. And then we'll let r expand to see if the minimum still exists and are the same no matter how big of an r you have. And if it does, that is for no matter how big a circle you draw for the domain, the minimum is still exists and are the same. That means the minimum exists for all, for the entire plane. So that's how that works. Now to establish, first let's to apply theorem 1, we're going to draw a limited circle, okay? And so we're imagining this on a limited circle of radius r. And to use that more conveniently, given the function the way it is with all the fourth power and square power and all that stuff, we're going to use polar coordinates to make things a little slightly easier. And so let's convert the function into polar coordinates, okay? And that would, you will notice quickly it becomes this thing right here. All right, so let's turn the page. Now that we have so then on now we imagine it being on some kind of fixed circle with a large radius, such as r0, okay? On the circle r equal to r0, then first we're going to prove that this thing right here is, cosine fourth plus sine fourth, is going to be bigger than or equal to 1/2. All right, is it bigger or less? I don't remember. Let me check. Yeah, bigger than or equal to 1/2. And so to prove that, see, I have a proof right here. Please try to prove this yourself. As you pull some stunt, and then I think you might have to use the half angle formula or something. Well, whatever. The point is, it end up being true. Okay, and so please go through the proof yourself, and then and the conclusion is the sine fourth plus cosine fourth is at least 1/2. It's bigger than or equal to 1/2, and that means. That means the first term is going to be on the circle. Now we're considering this a big circle with radius r0. So then the first term is going to be at least is r4. We're talking about this thing right here. So this thing is going to be at least r4 over 2. Okay, just this part. And so that is what the book says. Okay, is at least r4 over 2. Right? Let's see where to go. Right here. Okay, and therefore, now we're gonna let r0 equal to 2, okay, for starters. So for r0 equal to 2, when you plug in the values, then the function is at least 2 to the power 4th, okay, and divided by 2. And then minus 4, let's check what the function says. Yeah, minus r squared, which is 4, because r is 2 right now. And then plus 1. So that's the function is going to be bigger than or equal to that value on when r equal to 2, right here, which end up being 5. And then so then if f being the f of the function, in other words, the function on the boundary is pretty big, right? At least 5, whereas the function as 0, if we plug in 0, 0, we get 1, and therefore the absolute minimum exists. So right now we're shooting for the minimum. Now the absolute minimum exists where? Within the circle r equal to 2. The radius is the radius 2 circle. And then as a result, then so we will take the partial derivatives of the original function, not polar coordinates, just the original function, which will give us quickly that this set of solutions, and they look symmetrical, okay, and eventually you will notice that they will yield you some where x equal to y or plus or minus y, something like that, and then you will be able to come up with 9 and plus x and y equal to 0 also fits. So then you will quickly find out that it equal to the points, 8 points plus origin, so it's plus or minus 1 over square root of 2 to solve this equation. And then it is plotted out. Okay, here's all the possible minimums. See, it has 4 bumps. The graph has 4 bumps on the bottom. They all sit on the value of, they all have value of 1/2, I believe. So I drew a circle here. Let's move this over a little bit. Okay, so that's the graph, and as you can see, it has 4 bumps that are identical, and then the middle at the origin, it goes up a little bit. Okay, and that is so the origin is, but never mind the origin. If we have, so f is equal to 1/2 at all those 4 bumps. So then, so as a result, those four are the minimums, right? Their value is 1/2, as my circle here shows. And you can see that the 1/2 touches all 4 bumps at the bottom. And then, and so at this point, we're saying that f that therefore is bigger than 1/2 in the circle r equal to 2. However, our r equal to 2 is going to apply if you increase r to be, well, basically any value. Okay, if you repeat this process, the same solution will apply. As you get r, it gets bigger and bigger, the function is still going to be big along the boundary. In fact, the bigger r is, the function gets huge. Okay, it just shoots straight up because after all, it has x and y both to the power of 4. Okay, so then it just goes straight up, and as a result, the 1/2 is the minimum of the function in the entire plane as you let r go to infinity. And still, we are still able to use theorem 1, even though theorem 1 is only defined for a bounded region. So we just, but the bounded region has the same minimum no matter how big it is. Okay, so therefore, it's the minimum applies to to the entire plane. So that is, that's example 4. So please draw that yourself as well, if possible. And let's move on to the next part. I forgot to show you that I did write down the absolute proof for this. That is, if the function f minus f at the origin is going to be this thing, or bigger than this thing, okay, which is equal to, if you factor out, equal to this, and this value is going to be bigger than 1 as long as r0 is bigger than 2. And therefore, the function is always going to be big. Well, anyway, the function is always going to be bigger, therefore the origin value is always going to be less. And yeah, well, that should be good enough. I mean, this function is obviously increasing without bound. Next, let's look at some problem on 124. Okay, this isn't even called an example. It is. It's called a familiar problem. And that we're going to consider something called a rectangular parallelepiped. Now, what is that? That is a box, okay, a regular box. Anyway, the rectangular parallelepiped has a fixed surface area, and we need to maximize its volume. Okay, so let's see how we're going to do that. Well, first, of course, we have the volume. The thing will be, the dimensions will be x, y, z. Okay, so the surface area will be subject to x, y, y, z, z, x equal to 1. And let's just call it 1 and to make life easy for now. And then the volume, of course, is x, y, z, which then translates to, if we pull one of them, and like pull z out, then it equals to the function of the volume, right, equals to this, with the constraint of the surface area involved. And we need to figure out the maximum of this thing. And the restriction is x is bigger than 0, y is bigger than 0, and x times y has to be less than 1. Okay, the reason x times y has to be less than 1 is because if you redo the equation of the surface area, xy is 1 minus yz plus zx, which are both positive values, right? So it better be less than 1, otherwise it doesn't make any sense. In fact, when x of y equal to 1, the function is going to be equal to 0. See, here's x, y equal to 1 graph here. So that our region, the domain is in this area right here. However, you notice that our domain is not bounded, right? So, and more importantly, if x or y equal to 0, then I mean, if x or y equal to 0, the function is 0. If they're both 0, then the function is not even defined. Okay, so then the domain cannot include the origin. Okay, so what are we gonna do then? What we're gonna do is we're gonna restrict the domain. Okay, we'll think about it in the limited area, which is only makes sense actually. So here's how we're going to restrict the domain right here. We are going to restrict it as by the graph xy equal to 1, okay? The line y equal to h, the line x equal to h, here's y equal to h this way, h equal to h that way, and some line x plus y equal to d to get rid of the origin. So our domain now is in this thing right inside right here. So we cut off the top, the extra part on top, the extra part on the side, and the origin to get this thing. Okay, and that will be our restricted domain for now. And h, we can make h as big as we want, but right now h is a fixed value of fixed large value of some sort. Now, if we do that, then here are the situations that's always true. First, x plus y is always bigger than x or y, right? Because they're both positive numbers. And then 1 minus xy is always less than 1. Yeah. Anyway, so as a result, we can quickly calculate the f of xy, being that it equals to this thing right here. Then we can quickly calculate based on the 1 minus xy less than 1 business is going to be f of xy is going to be less than y or x, okay, by the same logic, because the situation is symmetrical here. So, and then certain other details we need to figure out. First, on the line x equal to h, the boundary of the new region, we'll call it R, okay, this weird looking thing. On this boundary x equal to h line, we will have f of hy is going to be less than y, okay? And y, since x times y is less than 1, then x is less than 1 over y, and y is less than 1 over x. So then as a result, y will be less than 1 over h, because right now x equal to h. So that's where that come from. Similarly, on y equal to h, f of x h is going to be less than 1 over h as well. Now look at how neat that is. You know, somehow you beat around the bush and something neat came out. So f of x y h, f of hy or f of h h are both going to be less than 1 over h. Okay, and then on x plus y equal to d, f of xy, which is less than x, we had that here, which is less than x plus y, being that they're both positive, which is equal to d, okay? So on the x plus y plus d, f of x and y is going to be less than d. All right, so far so good. So next, we are going to choose h as a big number, let's say 16, and d, and we'll choose d as 1 over 16, so that they're related. And then, for our region R, so then f is less than 1 over 16 on the boundary, because we just said so, okay, less than d, and then f is also less than 1 over h, which is 1 over 16, and y on the y equal to h line, f is f is less than 1 over 16 from here or here, okay, and then on the xy equal to 1 line, f is simply 0. I think we had that from earlier somewhere, okay, and then let's see, where is it? Well, wherever it is. Anyway, it is 0. So then that proves that f of xy is going to be less than 1/16 on the entire boundary of the region R that we just defined. Yeah, I just want to make sure that, yeah, see, if x y equals to 1, the function f is simply 0. Okay, we have it written down right here. And anyway, next, we are going to look for 2 points that's inside this region. That is 1/2, 1/2. Okay, 1/2 is contained inside this region because 1/2 times 1/2 is 1/4, which is less than 1, so it should be in here somewhere. Okay, and the value, once you calculate whatever f was, what was f again? X, y, something, yeah, right here. Okay, once you calculate this value happens to be 3/16, which is bigger than 1/16. So we have now satisfied the condition of theorem 1 in region R, okay, in our little weird looking region. So by theorem 1, the absolute max exists in the region R. So we can calculate it by setting f1 and f2 equal to 0. So once we do that, we'll take the first partial derivative, which I cranked it into the calculator. Okay, I wasn't about to do it by hand. So I got something like this. I think this is just the numerator part, okay? And well, there's some denominator, we'll ignore it. So anyway, the numerator part end up being something like this. And then which is not too hard to see, that's x equal to y, which will be equal to 1/3. And then which means x, y, z equals to, well, z also equal to 1/3 because the whole thing is symmetrical, right? And so then they all equal to 1/3. The volume is this thing, okay, which is also what the book says. Yeah, so then see, so the minimum in that weird little looking region would be it would be with this thing, which is what I wrote. Now the next point is that we are going to expand the way I want to do it is that we're going to expand the function, the 16 business and 1/16 to bigger and bigger to, you know, indefinite amount. And the same principle will continue to apply, that the function is the way the function works, okay? Right, so then as a result, we can pick a bigger number than 16, and as a result prove that the function is, this thing applies even as you get bigger and bigger. And therefore, that is the minimum on the entire plane. Now except for the points that it's not even defined, of course, on the entire, positive area, or the part of the plane we care about. So then, and that is the entire thing like this, not counting any part that is not defined. Now the book wants us to prove that the function actually is limited on those regions as well. But let's just say that we can choose the number big enough, okay, expand it, just like the previous example. We're simply going to expand our region, and being that it's we can choose h to be as big as, to be arbitrarily big, and then d then be 1 over that value, and the whole thing will work out the same way, okay? In fact, the bigger it is, the better it works. So then the whole thing should work out. And that's all I'm going to do, okay? I'm not going to care to prove that f is whatever in the other regions. Right. And anyway, so f is, let's see. Anyway, in that case, then this decided solid had, well, okay, next, let's look at the next part. That is, so far we have, pulled z in terms of x and y in this function here, even though there's no real reason to. I mean, they're all the same, right? They're all equal in standing. So the other way we can do this is using the partial implicit differentiation that we did in, what was it, chapter 1 or something? And then, and pull this stuff off, which I did here. Please do this yourself as well. Where is it? I think this is it. Okay, so the partial, so if we're going to take partial derivatives, then remember what we did in, what was it, chapter 1 or something, where we have a function, okay? We'll imagine that z is a function of x and y. So x and y are the independent variables. Z depends on x and y are independent, so they don't depend on each other. So we'll take the partial derivative of this function with respect to x, something we did many times in chapter 1, but we'll do this again, okay? And that gives us something like this, from which you get partial z, partial x. Similarly, partial z, partial y. And then the function itself we will also take the derivative and then plug in the partial z, partial x in there. That gives us a bunch of equations from which we eventually figured out that z, x, y are all the same, and they have to be equal to 1 over 1/3. Now that is, that when you look at this, that doesn't really look any better than what we did previously in the, before, by isolating z. So it's it doesn't really look like a benefit of any kind. So anyway, so that's that, and which is what your book did as well. Okay, it's just the implicit method, which also gave us the same answer, but is it better? It's hard to say. I think this, well, I don't know. Anyway, it's there. Okay, there are two ways to skin the cat, and it's hard to say which is really better. Okay, so now we have come to the end of this section, and let's look at the homework. For homework, on page 125, please do problems 1, 2, 3, 5, 6, 7, 9, 10, 11, and 15. Problem 11 is a bit tedious, so but please tough it out, okay? And it's worth the effort, I think. And just even though it's like you want to give up, is quite tedious. So, but knowing that, you go in it with make sure you got enough energy and time when you attack that thing, and then hit it. And problem 15 is not tedious, and I rather like it. It's quite nice. And so yeah. So please do that, and when you're done, I want to talk about them. So first, let's talk about problems 1, 2, and 3. These problems are all symmetrical, so I just wrote down the answer. I didn't bother doing them. I mean, if x plus y and z equal to 1, and everything is, the maximum would be they're all equal. Okay, similar to problem 2 and 3, they're just cubes. And then so that's that. So next, let's look at problem 5. All right, problem 5 is slightly more interesting. We have a function, and we're going to pull the same trick that we did in the example earlier, where we are going to draw some. We're going to prove that this thing has a minimum, and so for problem 5, we only have to show that the minimum exists. Okay, and then so to show that the minimum exists, we're going to pull the same trick as in the book, except that in this case, we don't have to worry about the domain going nuts. So I just drew a regular domain, say 8. I picked the number 8, and so we draw a square, and where each line is x equal to 8 or minus 8, y equal to plus or minus 8, and then I figure out the value of f as 0 is 4. And the value on the line plus or minus 8 is going to be bigger than 4, okay? And then similarly, the value on the line y plus or minus 8 is also bigger than 4, which means that the value as 0 is less than the boundary, the value of the function on the entire boundary of R equal to 8, which is what I chose. Which means by theorem, what was it, 1 or something? And it means that our absolute minimum exists inside this boundary, and so that is problem 5. Problem 6, we need to calculate the absolute minimum, which is pretty easy to do for this function. Let's see. Yeah, so after some cranking of something, then we calculate that the absolute min exists at plus or minus 1 and 0. Which is two separate points, okay? And then at 0, 0 is sort of a little absolute max, but it's not a min. And so then that, that's about it. And I plotted this graph out just to look at it, no reason. As you can see, there are 2 absolute mins down there, right? And then 0 is the, what is that? The local max. Okay, it's not the absolute max, it's in the local max, and I plotted the points here to highlight the function. And there's not much to this. You can plot this if you want. It's not a big deal. So next, let's look at problem 7, which is a matter of, we're supposed to find the absolute max and min. Well, this problem has a y equal to the 3rd power, which means that if you hold x constant, doesn't matter what, as y goes to infinity, f is going to go to positive or negative infinity, okay, in the opposite infinity of where y is going because of the minus sign. And therefore, the absolute max or min does not exist for problem 7, and that's that. Next, let's consider problem 9, where we're gonna build a box inside a ellipsoid. Okay, so I decided to do that. So here's what I drew here. We're gonna follow the process, okay? And so here's a box inside the ellipsoid, and remember the box, I will call the corner of the box XYZ, and therefore the volume will be 8 times XYZ, because this thing comes in, 8 chunks like this. And then so we're going to calculate 1 XYZ and then multiply by 8. So the ellipsoid's formula is given as such, okay, from calculus, I don't know what, 3 or something, or 2 or 1, or pre-calculus. I don't remember when we learned this. But anyway, so we are going to follow the partial derivatives plan. What is this? I think I'm doing the implicit trick. You can do either one. The implicit one might be better because of all the squares. Either way, okay? Let's take the partial derivatives and then calculate partial cx and partial cy, and then plug something in and stuff, okay? And then eventually something equals to 0 here, and then we end up with this kind of stuff. It's just a matter of performing standard procedure. Okay, and so next page, right here, keep going. We have the bunch of stuff, something equal to something else, and eventually you will get this symmetrical relationship. Z equal to C over square root of 3, X equal to A over square root of 3, Y equal to B over square root of 3, very convenient, right? And V is 8 times, don't forget the 8 times, which is equal to that, and which does check out. That is the answer in the back of the book as well. So that is for problem 9. It's fairly straightforward. Because everything's symmetrical and looks nice. Now problem 10, I want to talk about it in some detail. What does problem 10 say? Okay, we need to find the best dimensions of a tent with a horizontal ridge pole. Assume that the 2 ends close by isosceles triangles and there is no floor. Yeah, I just want to mention that I own like about a dozen tents, from the smallest one to the biggest one. Some are self-popping up. Okay, you just throw them down and out they come. And nowadays there is not a tent for sale that has no floor. That doesn't make any sense. But of course, this book is from 1947. And then back then they did things differently. And also, this says that we're going to build a tent according to maximize the volume, which doesn't ever happen. You build a tent according to the size that's needed. For example, the tent needs to be at least 6 foot long, right? So a guy can fit in there, for heaven's sake. And yeah, but having said that, right. Anyway, so having said that, and that's that. And in case you're wondering, I don't go camping. I own a bunch of tents because I like playing with them. But anyway, so let's calculate this thing according to the way the book wants. Okay, so we're gonna go about it, well, the same way everybody does, right? The area of the tent, we will gonna call it is obviously this, what is this? Okay, this is method 1. I tried 2 ways of doing it. Here's method 1. All right, so area of the tent is obviously something like that, right? And you have some relationship, and we need to max out this thing. And so we plug various things in, and in my case, I end up with quite a complicated formula. Okay, which I then typed it in, and for which I have to calculate the derivative, because by now we're assuming that the maxima exists. So now we just have to calculate it instead of having to do that weird trick where you have to prove that the minimum or maximum actually exists. So let's say we'll just say that it does. And then so we calculate f1, and I only wrote down the numerator here, okay? Because the whole thing, I mean, look at this. The whole thing is very long and a headache. I plugged it in. I mean, typing it into the calculator alone took a long time. And then here's the f2. Just the numerator part, and everything looks quite complicated, but anyway, I was able to from this relationship right here, okay, I was able to come up with x equal to square root 2 of y, which does make things easier. And eventually, I plugged that into the function and was able to, well, it didn't really help much. The point is, you gotta work on these two things until something comes out, which is what I did here. Okay, eventually I was able to come up with this: y equals the square root of c over square root of 3, and x is I don't even know where it is. X is right here. Okay, y is right here, and h is right here, and then yeah, the ratio of h over y is 1 over square root of 2. And then as a result, the tent's top angle is 90 degrees. So for the maximum, the angle of the tent happens to be 90 degrees. The only reason I even say this is because I looked at the answer, and my answer is correct. But the answer is presented like this, whereas the volume equals to, yeah, that thing. Yeah, so I will show this to you here. Maybe pull back a little bit, show you the top part. Where's the top part? Right here. Okay. So I'll show you the whole thing, and I'll let you decode what I say here, because I barely understand it myself. It's such a mess. Okay. So I was done, and I was quite pleased with myself that I was able to plow through all that mud. But afterwards, in the book answers something about the angle at the top is 90 degrees. It got me thinking, maybe I took the long route by accident. There might be a faster way or a cleaner way of doing this, so that you don't have to walk through so much mud. So I consider the angle. Okay, so as a result, I did the method 2. Let me find it. So here is my method 2, which in which case I calculate the same thing. But this time we're going to use the angle, okay, which I call theta, and the fact that it has the isosceles triangle business, which come to think of it, in the first method, I don't even think I cared that it's isosceles triangle. Maybe that's why it was such a mess. Anyway, so I used the fact that it's isosceles triangle, and then the length of y, and then I wrote down the formula accordingly, which I got this stuff, okay, yeah, and then plugged in some kind of v by isolating y, and so our then the volume then equal to this thing, where c is just some constant. Let's see. Oh, I forgot to show you. In my first method, I did in the first method, what I did is that I pretended the constant is some value, 10 or something. I don't know. Anyway, so I used the graph to finish. The reason I was able to get through that mess in the first method is because here's what I did. See, I plotted the graph onto the calculator to double check that my answers are correct. And I was noticed that there really is a maximum, okay, and it's somewhere there. When I think I let the constant, what was it? What's the constant in here? Area or something? Yeah, I let the constant be 10 so that I can plot it in this thing. Anyway, so I used an example and plotted it in here to make sure that my formulas are correct. You don't have to do this. I just showed you why I was able to get through all that mud. Because normally I'd be so confused and I would just want to give up. Plus I don't know if I messed up somewhere, right? If I messed up, then I'll never get the right answer, and I'm inside all this mud. But the Desmos calculator, once I was able to plot it and see that it does look right and things check out, then it gave me more confidence to get to the end of the mud puddle, and then I came out looking peachy. So, so let's continue with method 2. Okay, now method 2, doing the same thing. You notice the volume is a whole lot better looking than method 1. Okay, at least in terms of trying to do some kind of partial derivative. So I took the partial derivative and I got this thing, which I got that first relationship, okay, which is good. And then I took the second partial derivative with respect to theta, and I came up with something weird, okay. That is, I came up with this. That is, I already said 3x squared, etc. equal to c. And now the second equation, I got 2x squared equal to c, which is not possible. I already said is three of them, right? How can they be this? And then I realized that that's because that answer is to be rejected. Now to reject that answer, that means this equation to be 0. That means the factor cosine theta has to be 0 to make this thing 0, because the other thing is definitely not c. Okay, so if cosine theta is 0, then theta is pi over 2, like the book says, and like I calculated earlier. And then, by the time you calculate from this relationship right here, then we got x equal to the square root of c over 3. And then everything else come out looking exactly the same. But as you can see, this answer is so much superior than the one I just did. Okay, which is also probably what the book did, which is why the book mentions that the angle of the tent is 90 degrees, which yeah. So I am so this answer is much nicer and easier. Though I don't regret having done the first answer, because it was nice using decimals, and I was at first stuck and puzzled, and then was able to get myself out of the mess. So that was nice also. And normally I wouldn't ask you to or I wouldn't ask myself to do 2 methods for the same problem. But in this one, I feel that it is justified and also worth it. So please, you don't have to do method 1, okay? But please at least try method 2, whether you used it or not, because it is a much nicer, cleaner, and more pleasant way of doing things. And you will particularly enjoy it if you had gone through a pile of mud like I did. Okay, so next, that's problem 10. Now problem 11 sounds standard. We need to maximize the sum cylinder with two cones, one on each end, fine. So we know how to write down the standard formula, and then take the partial derivative, set it to 0, and plug stuff up, and plugging stuff out, and call it done. That is the idea, and that is what I did. Now here is the formula, right? Which is we can quickly come up with the volume, and once you get everything written out like it's supposed to. Yeah, there usually isn't much to it, except that the volume of the cone is 1/3 pi r squared times height, as you might recall. So that's that, and then things went into a headache once I did the partial derivatives, which I actually I just typed this thing in the calculator, okay? And here y stands for h, because the Symbol Lab derivative calculator doesn't accept y, I don't think. Anyway, so I typed it in. Remember, y stands for h in this formula. And then I looked at this, and I feel like my head is gonna hurt. I don't want to plow x and y or h out of this mess. Look at that. It looks repulsive. So I was staring at it. I wondered if there's a better, faster, easier way to get out of this. And so I stared at it for a long time and beat around the bush. I even tried, as you can see here, I tried to use polar coordinates. That turned out to be even worse. So forget that. And then so eventually I asked AI, okay, how do you do this? Because I sure don't want to mess with that mess. And AI says, you have to mess with the mess, basically. But the AI says something interesting. That says that the x and h actually has a very simple relationship. It claims that, so it said x equal to 2h or something like that, which is not true, but it gave me an idea. So then I stared at this thing more closely, okay? And then was able to figure out of all this, that x and h, it does equal to, it has a simple relationship, which makes life much easier. From here, you just draw the triangle, okay? And then and you quickly come up with this proportion. Now, so that's the x and h and x, and x plus h can be represented in terms of h or x, okay? And so once I do that, does that make life better? Not really. Now I have to plug this thing in here. And look at that thing. That thing gave me another headache. So I thought I should try to get around it somehow. But in the end, I couldn't get around it, okay? I mean, finally, yeah, so at the bottom here, what I did is I plugged the value of x or h or something into the original function for v. And then I took the derivative, hoping that I can come up with an easier v of x than that, but it's not that much easier. So I look at this thing, that does not look easy. And I'd rather just do something easy, okay? I'm really not into doing really tough stuff. But after I stared at it long enough, I couldn't figure out any easier way to do it. And I look at the answer, and the answer is very short, but it's not simple, okay? The answer has a bunch of weird powers, square roots, fourth root, and then square root to the third power, all that stuff. So finally, I just decided that I'm just gonna have to, suck it up and do that. So that's what I did. Eventually, I figured out what x has to be, okay? By doing the derivative, I figured out that x squared equal to all that stuff, which I really did not want to do, but there was no way out of it. So I figured out that x squared equal to this thing, x equal to that thing, and x cubed equal to that thing. And then that all that has to be plugged into the v. Where's v? I believe right here. Yeah, this is v. Okay, so I plugged it all into the v, and I got this answer. And you say, where did you plug it in? I plugged it in with a simplifying calculator on the internet, and let me show you. Now, before I show you my simplifying equation, let me show you what I plotted. See, I plotted this thing with the graph, that's the orange surface. Okay, as you can see, it does have a highest point. And then I plotted the two derivatives in there, and as you can see, they do reach the highest point when you set the two equations equal to 0. And in fact, the second equation is equivalent to this thing. Okay, they are the same, and which is how I knew that I got this one right. So I can tell that my equations are all correct because they all pan out. I let the constant c equal to 20, which is also the book calls it A. That is the total area. Okay, in order to plug in to have the calculator have something to work with, but I still didn't at this point. I still couldn't find what the value of the thing is, right? So then, as a result, I was stuck with doing the actual grunt work, like I showed you, to find what x is. And once I found x, then I was able to plug it in. And well, then I wasn't going to plug anything in. Okay, and let's see, what is that? Okay, so I plugged it in on the calculator, as you can see here. The calculator where y here stands for c, okay, or a, which is, I say right here, y equals c or a. It stands for the total area. So I put that in there, so the calculator, the Symbol Lab has a simplify option, so please use that yourself as well if you don't want to go through this much work. So I plugged all of this stuff, typed it all in, okay, and made sure I didn't get anything wrong, and it came up with this answer, and that is exactly the answer at the back of the book. If you pretend that y equals to a or c, the total area, then this is exactly it. So I got it. So I got it right, okay? I wasn't gonna, that's the first time in my life I used the simplify function in the calculator. But I figured this is definitely worth it. So here is what I wrote. So I copied that down, okay? That's exactly what the end of the book says. Yeah, so I guess well, of course you can say that, well, if I'm having such a tough time doing this, what happened to the people in the past who didn't have all these calculators? Well, I think the people in the past are just tougher than me, that's all. Yeah, I do not like doing all this stuff, grunt work, but I did it because there's the answer is very close. It's like I'm like Indiana Jones when he was hanging off the cliff, and there's the goblet of what was the Holy Grail, right? It's just within a few inches of his reach, and he really needs to get it, and that's how I feel. I don't really want to do this, but the answer is so close, and I can't just give up. So I was forced to do it. Anyway, so I got my answer, unlike Indiana Jones, who could have died if he didn't give up. Anyway, but he did, of course. So let's look at problem 15. The problem 15 is a cute little thing. Okay, we already know the answer to this. I mean, we've done this at some point, right? The triangle of maximum area that can be inscribed in a circle. Well, we know what that is. I don't know when we did this, but I'm pretty sure we did this at some point. But the book, the reason I want to do it It's because the book made an interesting suggestion that I don't remember necessarily thinking of back in the day. That is, we're going to draw the triangle like this. Okay, we'll put the triangle and have it centered at the origin in such a way that it has its distance from this center. From each vertex of the triangle is the same distance. We call it A. Now that is a formula in geometry. Okay, there's a point, I can't remember what it's called, centroid maybe? I'm not sure. And how is that point achieved? Maybe by dividing the angles equally and the intersection, maybe, or something else. I don't remember right now. The point is there is such a thing, okay? And that's what we care about. That is, you can find the center of a triangle that is equal distant to each point of this triangle, okay, each vertex. And so I drew it this way, and then the area then becomes very simple, okay. And so here's the area, and then we need to, and then the three angles, of course, add up to be 2 pi. Now at that point, then the whole formula just comes out very simply, which I will show you on the other side. Okay, we take the partial of x and y. Now I'll call the angles x and y. And at this point, which we quickly notice that being that they're symmetrical, x has to equal to y to satisfy both equations, and which we quickly find out that x is 2 pi over 3. And therefore the triangle is, and so is y and so is z, and therefore the triangle has to be equilateral. As we already know from previous experience. And that should be the end of this section.